Today we're breaking down a really critical paper from Anthropic, Constitutional Classifiers plus to cheese, efficient production-grade defenses against universal jailbreaks.
Yeah, this one is a big deal. It's basically a roadmap for taking a safety feature from a promising but, let's say, expensive academic concept to something you can actually run at scale.
So for anyone just tuning in, let's do a quick 1-minute summary of what they achieved.
Okay, so the core idea is they took their original constitutional classifiers and made them viable for production with three key innovations. First, they introduced what they call exchange classifiers. These look at the entire conversation, input and output together, to stop clever attacks that try to hide context.
Got it. What's the second one?
Second, they built two-stage classifier cascades. Think of it like a triage system. A cheap, fast classifier screens everything, and only the suspicious stuff, maybe 10% of traffic, gets sent to a more powerful, expensive classifier.
Smart. Adaptive computation.
Yeah.
And the third?
And this is the really clever part. Efficient linear probes. These basically reuse the computations the language model's already doing. So instead of running a whole separate model for safety, you just peek inside the main model's brain as it's working, which is incredibly cheap.
So what was the final payoff, the big result?
It was huge. The final system gave them a 40x reduction in computational cost over their first robust baseline. And at the same time, the rate of incorrectly flagging harmless queries plummeted to just 0.05%. In their red teaming, no one could find a universal jailbreak for their highest risk targets. It's robust and efficient.
Okay, that's a fantastic summary. Let's unpack that, starting with the context. Why was a system like this so necessary in the first place? What was wrong with the last generation?
Well, it all comes down to risk mitigation.
Yeah.
You're dealing with models that can generate incredibly detailed information, and the biggest concern has always been things like CBRN. That's chemical, biological, radiological, and nuclear threats.
Right. If your model can be tricked into explaining how to make something dangerous, you just can't deploy it.
Exactly. And the previous generation of these constitutional classifiers, while a good idea, had these two massive deal breakers for production.
The first one being cost, I assume.
Oh, absolutely. The old system had a 23% computational overhead. I mean, imagine telling your CFO you need to increase your compute budget by nearly a quarter just for a single safety feature. It's a non-starter.
Yeah.
A total budget killer.
And that's just the financial cost. The other problem was user experience, right? The false positives.
Yeah, the refusal rate was 0.38% on production traffic. Now, that sounds like a tiny number, but if you have millions of users making requests, that's thousands of people every day getting blocked for no reason.
And they get frustrated, they complain, and eventually the engineers might just turn the feature off because it's causing too much friction.
Precisely. So the old system was too expensive and too annoying. And on top of that, attackers were already finding ways around it.
So let's talk about those attacks. The paper mentions the previous dual classifier architecture, one for input, one for output, was vulnerable.
That's it. It's this constant arms race. And their adversarial testing found two major classes of attacks that just, walked right through that old system.
Let's get into those because they really set the stage for why the new architecture was needed. The first one you mentioned was reconstruction attacks.
Yeah, think of this like giving the model a puzzle. Instead of asking for a harmful procedure directly, you ask it to do three seemingly harmless things, like write a Python function called stepone that returns string A, then another for string B, and a third for string C.
And each of those strings is a fragment of the dangerous instruction.
Exactly. The input filter sees three benign coding tasks, but then later you ask the model to combine the outputs, and suddenly you have the full harmful instruction reconstructed. The input filter is completely blind to the real intent.
Because the intent is spread out. Okay, and the second major attack type was output obfuscation.
This is where the model gets jailbroken, but it hides the answer in plain sight using, say, metaphors or coded language.
Can you give an example?
Sure. You might successfully prompt the model to describe a chemical process, but to call the reagents food flavorings and the equipment kitchen supplies. The output classifier just sees a weird recipe. It has no idea what's really being discussed unless it can see the original malicious prompt that set up the code.
So without that context, the defense is useless.
Right. And people might think, well, these kinds of jailbreaks must degrade the model's performance, right? This jailbreak tax.
Yeah, the paper mentions Claude Opus's accuracy on a benchmark dropping from 74% down to as low as 32%. Doesn't that make the attack kind of pointless?
You'd think so, but the key word there is variability. It dropped to 32% in some cases, but only to, say, 49% in others. That variability tells you that a cleverer attacker can probably find a new method that preserves most of the model's capability. You can't rely on the attacks as your defense. You have to close the loophole itself.
Which brings us perfectly to the first big innovation, the exchange classifier, fighting context-dependent attacks with a context-dependent defense.
That's the core architectural shift. They got rid of the separate input and output classifiers and replaced them with a single unified system.
And how does it work differently?
It monitors the conversation continuously. So as the model generates its response, token by token, the exchange classifier is evaluating those tokens in the context of the original prompt.
So in that metaphor example, it would see the prompt asking for a chemical process and then see the output talking about food flavorings and immediately connect the dots.
Exactly. Obfuscation becomes exponentially harder because the classifier has the key, the cipher, right there in the prompt. It can see the connection.
Okay, that sounds way more robust, but it also sounds, well, expensive. You're running a powerful check constantly.
And you're right, that was the trade-off. This first version, using a haiku-sized model as the classifier, actually increased the safeguard cost by 50% over the already too expensive old system.
So they solved the robustness problem, but made the cost problem even worse.
Temporarily, yes. But the red teaming results proved they were on the right track.
What did that show?
The results were stark. The system had 2.2x fewer high-risk vulnerabilities. The rate at which red teamers could find a flaw was cut nearly in half.
And I saw a fascinating stat in there about the effort required.
Yeah, this is huge for production security. To find the one universal jailbreak against this new system took a researcher 100 self-reported hours. On the old system, it was more like 27 hours. That's a massive deterrent.
So, okay, they've got a system that works, but it costs a fortune. That's the next engineering problem to solve.
Precisely. And the solution was adaptive computation, the two-stage classifier cascade.
This is the triage idea you mentioned. Stop running the expensive check on everything.
Exactly. You put a very cheap, lightweight classifier as the first stage. It screens everything. Its only job is to ask, is this even remotely suspicious? It doesn't make the final call.
So it can have a higher false positive rate because it's not actually blocking the user, it's just escalating.
Right. And it only escalates about 10% of the traffic. That 10% then goes to the much more expensive, much more accurate second stage classifier, the big guns.
And that second stage classifier is the one that makes the final decision to refuse or allow.
That's it. And the impact on cost was immediate. This two-stage system, plus some other optimizations, delivered a 5.4x computational cost reduction compared to that single expensive exchange classifier.
A huge win. But they didn't stop there. There's still a bottleneck.
There was. And it's an interesting insight. When they looked at the cost breakdown, that lightweight first stage was still responsible for about 77% of the total system cost.
Because it has to touch 100% of the traffic.
Exactly. So to get to truly production-grade efficiency, they had to make that 77% figure basically disappear.
And this is where the linear activation probes come in. This feels like the most elegant part of the whole paper.
It really is. The concept is, well, it's brilliant. As your main LLM is generating a response, it's creating all these complex internal representations in its hidden layers. You can think of them as the model's thoughts. An external classifier is like hiring a separate security guard to watch what the model says. A linear probe is like tapping into the model's own internal security system that's already monitoring its thoughts as they form.
You're reusing work that's already being done?
Massively. The computational difference is staggering. A small external LLM might take 8 billion FLOPs to check a token. The probe takes about 377,000 FLOPs. The marginal cost is effectively zero.
But just reading the activations isn't enough, right? They had to make some specific training modifications to make this work for streaming, token-by-token classification.
Correct. Two big ones. The first is called Sliding Window Mean Logit Smoothing, or SWIM.
What problem does that solve?
It solves the spikiness problem. A model might generate a single word that looks bad out of context, and a naive probe would immediately flag it, causing a false positive. SWIM averages the probe's predictions over the last 16 or so tokens.
So it only fires if it sees consistent evidence of harm, not just a random blip.
That's it. And the second modification, softmax weighted loss, is just as clever. It addresses the harmless prefix problem.
Which is what, exactly?
Imagine a user asks a bad question, and the model starts its reply with 5 sentences of, throat clearing and warnings before it gets to the one harmful sentence at the very end.
A normal loss function would penalize the probe for correctly identifying the first 5 sentences as harmless.
Exactly. This weighted loss function basically tells the training process. Pay most attention to the parts where the probe is confidently predicting harm. It lets the probe be right about the harmless prefix without getting confused.
So these two things together make the probes fast and accurate for streaming.
Right. And what was really cool was that the probes weren't just a cheaper replacement for an external classifier. They were actually a better partner in an ensemble.
The ensemble effect, why was that? Why did combining them work so well?
Because they capture complementary signals. When they measured the correlation, they found that the probe's predictions were less correlated with an external classifier's predictions than two external classifiers were with each other.
In other words, the probe is seeing something different. It's picking up on signals that the external classifier misses.
Precisely. It's looking at the rich internal state of the model, not just the text on the page. It's getting cues about intent and direction. By combining those two different views, you get a much more robust and accurate final decision.
And the trade-off curve in the paper makes this so clear. The probe classifier cascade wasn't just cheaper, it was also more robust. They got a 100x compute reduction on their CBRN test set while improving safety.
It's the best of both worlds. The dream scenario.
Okay, so let's put it all together. What did the final production-grade system that they deployed on Claude Sonnet 4.5 actually look like?
It's that beautiful two-stage cascade. Stage 1 is the super cheap linear probe running on all traffic all the time.
And if that probe's score crosses a certain threshold?
It escalates. And that happened for only about 5.5% of production traffic. That tiny fraction gets sent to Stage 2.
And Stage 2 is the ensemble of the probe and an external classifier.
Right. They combine the scores with a weighted average, 55% weight to the probe score, and 45% to the external classifiers.
Why the slight edge to the probe?
Because, as we just discussed, the data showed its unique internal signal was slightly more valuable for overall robustness. It was capturing that orthogonal information that really helped nail down the tough cases.
So this is it. The system is live. What were the final deployment metrics, the numbers that really matter?
This is where it all pays off. The flag rate on real production traffic dropped to an incredible 0.05%. Remember, the old system was at 0.38%. That's a huge reduction in user friction.
And the cost?
The total computational overhead was down to just 3.5%. They went from a 23% budget killer to a totally manageable 3.5%, a 40x reduction from their initial robust baseline.
Wow. And the final security audit, they threw over 1,700 hours of red teaming at it.
And it held up. The lowest vulnerability discovery rate they'd ever measured. The time to first exploit jumped to 30 hours.
Yeah.
And the most important takeaway, no universal jailbreak was found that could answer all their high-risk CBRN target questions. The system worked.
That is just a phenomenal story of iterative, intelligent engineering, from an impractical, expensive system to something this efficient and this robust.
It really is. It shows that safety doesn't have to be a trade-off against performance or cost if you're clever about the architecture.
So as we wrap up, what does this point to for the future? Where does AI safety architecture go from here?
Well, the paper itself suggests the next logical step is even tighter integration. Not just monitoring the model, but maybe using these classifier signals to directly influence the model's sampling process, nudging it away from harmful generations before they even happen.
So the guardrails become part of the steering mechanism.
Exactly. Or even training the models from day one to be inherently resistant to these kinds of obfuscation attacks.
Which leaves us with a really interesting question for you to think about. Will the future of AI safety be these kinds of external auditable systems that monitor a model? Or will safety become so deeply integrated and co-trained that it's just an inseparable part of the model itself?
There's a big trade-off there. External filters are easy to update, but integrated defenses might be fundamentally more robust. Finding the right balance will be, I think, one of the central challenges for the next few years.